technology comprised of our wits, fire, and sharp sticks for the most of our history. While fire and sharp sticks evolved into power plants and nuclear weapons, our brains received the most significant boost. Since the 1960s, the processing power of our brain machines has increased tremendously, allowing computers to get smaller while also becoming more powerful. However, this process is approaching its physical limits. Computer components are shrinking to the size of atoms. A computer is made up of extremely basic components that perform very basic tasks.
In October 2019, Google made a big announcement. Google said it had achieved quantum supremacy. That's the moment when quantum computers can beat out the world's most powerful supercomputers for certain tasks.
They've demonstrated with the quantum computer that it can perform a computation in seconds what would take the world's fastest supercomputer years, thousands of years to do that same calculation. And in the field, this is known as quantum supremacy, and it's a really important milestone.
Data representation, processing methods, and control mechanisms. Computer chips are made up of modules that contain logic gates and transistors. A transistor is the most basic type of data processor found in computers. It's essentially a switch that can either block or allow information to pass through. This data is made up of bits that can be adjusted to a value of 0 or 1. To represent more complicated information, multiple bits are combined. Logic gates are made up of transistors that perform extremely basic tasks. An AND gate, for example, sends a 1 output if all of its inputs are 1, and a 0 output otherwise. Finally, logic gates are combined to construct useful modules, such as adding two numbers. Once you know how to add, you can multiply, and once you know how to multiply,
let me start with this. You never hear your weather forecaster say, well, there's a negative 30% chance of rain tomorrow, right? That would just be nonsense, right? The chance of something happening is always between 0% and 100%. Okay, but now quantum mechanics is based on numbers called amplitudes. Amplitudes can be positive or negative. In fact, they can even be complex numbers involving the square root of -1. So a qubit is a bit that has an amplitude for being 0 and another amplitude for being 1.
Quantum physics, on the other hand, is complicating matters as parts get smaller and smaller. A transistor is nothing more than an electric switch. Electrons are charged particles that move from one location to another. As a result, a switch is a channel that can prevent electrons from traveling in one way. A typical transistor scale nowadays is 14 nanometers, which is about 8 times smaller than the diameter of the HIV virus and 500 times smaller than a red blood cell. As transistors drop to the size of a few atoms, electrons may be able to simply transport themselves to the opposite side of a blocked passage using a technique known as quantum tunneling. In the quantum realm, physics operates in a very different way than we're used to, and regular computers just stop working. For our technical advancement, we are reaching a true physical barrier. To tackle this difficulty, scientists are developing quantum computers that take advantage of these peculiar quantum features. Bits are the smallest unit of information in conventional computers. Qubits, which may be set to one of two values, are used in quantum computers. A qubit can be a single photon, or a two-level quantum system like a spin and a magnetic field. The conceivable states of this system, like photons with horizontal or vertical polarization, are 0 and 1. The qubit in the quantum world doesn't have to be just one of those. It can be in various proportions of both states at the same time. This is referred to as superposition. When you test its value, for example, by passing the photon through a filter, it must choose whether to be vertically or horizontally polarized. So long as the qubit remains unseen, it's in a superposition of possibilities for 0 and 1, and you can't tell which one it'll be. However, it collapses into one of the definite states the moment you measure it. The concept of superposition is revolutionary. At any given time, 4 classical bits can be in one of 2 to the 4th power of 4 possible configurations. There are a total of 16 possible combinations, but you can only utilize one of them. 4 qubits in superposition, on the other hand, can be in all 16 configurations at the same time. With each additional qubit, this number climbs exponentially. 20 of them are already capable of simultaneously storing 1,000,000 values. Entanglement, a close link that causes each of the qubits to react instantly to a change in the state of the other, no matter how far apart they are, is a really strange and unintuitive quality qubits can have. This means that if you measure just one entangled qubit, you can determine the properties of its partners without having to look at them. Qubit manipulation is also a brain teaser. A simple set of inputs is fed into a logic gate, which creates a single definitive output. A quantum gate manipulates superpositions as input, rotates probability, and outputs another superposition. So a quantum computer entangles certain qubits, uses quantum gates to change probabilities, and then measures the result, collapsing superpositions to an actual sequence of qubits. This means that you can perform all of the calculations that are possible with your configuration at the same time. Finally, you can only measure one of the outcomes, and it'll almost certainly be the one you want, so double-check and try again. However, by skillfully utilizing superposition and entanglement, this can be considerably more efficient than on a traditional computer.
Right, so nature gives you this very, very bizarre hammer in the form of this interference effect among all of these amplitudes, right? And it's up to us as quantum computer scientists to figure out what nails that hammer can hit.